All right, welcome everyone to Rocktober. My name's Carrie, I'm an educator here at the museum, and I'm so glad that you're able to join us today for this really exciting event as we celebrate Earth Sciences Week. So we are doing this talk in a very special way. We are broadcasting on our YouTube channel, and it will also be recorded, but we also have a live audience here in our Windows on the World Theater. So we have about 18 people, well, 20, including Jessica and I here in the room. So I would love to introduce our speaker today. So the title of our talk is the La Soufriere Eruption from 2020 to 2021. And our speaker is Thomas Christopher of the Montserrat Volcano Observatory. And so please, Thomas, tell us where that is, because it is in a very cool place. and you can take it away. So I did want to say that if you have questions, either in the theater or on YouTube, please, if you're on YouTube, put them in the chat. Chris will get the questions to me. He's out in the background, orchestrating all of this magic. And if you're in the studio, just raise your hand and I'll call on you. So, so Thomas, take it away.
Good afternoon. Yes, just to give you a bit of background on where Montserrat is. It's close to an island called Antigua. Antigua is fairly famous. We're actually 30 square miles away from Antigua, just to the southwest. So it's a 10-minute flight on a very tiny aircraft to get to Antigua, because that is our closest international airport. So we're more or less smack in the middle of Hurricane Alley, because it's about an hour flight south of Puerto Rico. So that's where we're located, in the kind of the bend of the arc. But as we go forward, I'll kind of give you an idea of the geography of the region and where the islands are. So you should have a better idea of what's happening. Now, just to give you a bit of background, the Montserrat Volcano Observatory exists because there was an eruption that started here in 1995. And that is basically why this island became known to quite a few people, because of this eruption, because it's 40 square miles, so it's not big, and there wasn't really much happening here, so most people didn't know about it. But after the MVO came into existence, we had this really drawn out eruption. This volcano has still been erupting since 95. So the observatory became a permanent fixture. Now, because of how it was set up, the observatory is not managed by the government of Montserrat. It's managed by outside entities, whether it be universities or institutions who know how to monitor a volcano. So currently we're being managed by the Seismic Research Center, which is a part of the University of the West Indies. So what that did, it basically united all of the volcanoes in the English-speaking Caribbean under one body. The French islands have their own observatories. So basically, the scientists that work between here and Trinidad have access to all of the volcanoes on every English-speaking island, and we are responsible for them. So when this volcano erupted in St. Vincent, people from here had to respond because it was part of our job. And I would have visited St. Vincent quite a few times in the past to take measurements from the crater, well, degassing measurements at least. The same can be said for Dominica and St. Lucia. So we try and monitor all the islands as often as we can, you know, to try and develop these background baselines. So if there is a problem, like there was in St. Vincent, then we have something to work with, some sort of reference frame to know how intense the activity may be at the time that we're seeing it. All right, so can we get started? All right, cool.
Yes, please do. Sorry, I muted myself.
Okay, so yeah, so the Caribbean arc. Now, basically, the Caribbean arc is a chain of volcanic islands, and the situation is very similar to places such as Japan or Indonesia, where you've got subduction of one plate beneath the next. And it generates melting, and molten rock, which is called magma, it's quite buoyant compared to rock, which is not molten. So molten rock has a tendency to rise to the surface. So whenever we see these island arcs or chain of volcanoes, we associate them with subduction zones. So as you can see in the Caribbean, we have quite a few, well, 19 of them apparently, which are potentially active. Now, one of the main differences between the Caribbean and places like Japan or Indonesia is the subduction rate. And that is quite significant because your subduction rate affects how fast you can generate magma. And how fast you can generate magma will affect the frequency of your eruptions and possibly the sizes of your eruptions as well. So in the Caribbean, we have a subduction rate of around 2 centimeters per year, whereas Indonesia is probably around 7 centimeters. I think Japan is probably around 9. So things are happening faster there. Earthquakes are more frequent, eruptions are more frequent. However, all of the things that we see happening in this part of the world, Japan and Indonesia, can happen in this region. These large earthquakes that, well, maybe or may not be able to generate a tsunami. It depends on the situation, or these eruptions. And the only difference here is that they're less frequent. And if you ask me, that is a problem, because when things are not happening frequent enough, people tend to get complacent or just not aware of what the situation is. So to be fair, the volcano in Montserrat last erupted 400 years ago. So no one here had a living memory of a volcano being here. So the eruption more or less took some people by surprise. You know, well, we had a volcano here. But I think now, since the eruption of Montserrat, people are much more aware of the situation in the Caribbean, and there's a lot more education in the region as to which islands are volcanic and what needs to be done. So as I said, you know, we have subduction going on. I spoke a bit about that. So what we have is the North American plate and the Caribbean plate. And what you see is that this chain of islands, they mark the edge of the plate boundary. So you can actually trace the plate boundary based on how these islands are located, or where they are located, albeit there'll be an offset of probably 200 kilometers away from the plate boundary. So as long as we've got this subduction going, we're still getting earthquakes and the odd eruption, because as I said, it's quite slow, the subduction in the region. Now, I just want to say something about volcanoes, because people would have seen eruptions on TV, and most people would have seen lava flows, like the picture in the middle. Now, the differences between a lava flow and a lava dome is simply chemistry. Now, there is a component of the magma which is called silica content, and that basically dictates how it behaves. It dictates the physical characteristics of these volcanoes. So for these volcanoes which have low silica, they generate lava flows. And as a result of that, these volcanoes tend to be less explosive, because you can release gas easily from these liquid magmas, as in opposed to these sticky magmas which generate these domes. And subduction zone volcanism, which is what we have in the region, we get these high silica magmas, we don't get lava flows. So inherently, our volcanoes are much more dangerous than the ones in Hawaii, because they tend to be more explosive. So we need to be aware of that. So even though within the whole dome situation as well, just to show you how subtle changes in chemistry can make a difference. On the left, I have these are domes from La Soufriere in St. Vincent. Sorry about the overuse of the word Soufriere. You can blame that on the French when they were in the region. They called every volcano in the Caribbean Soufriere. There are about 5 of them with the name Soufriere. So there's Soufriere Hills in Montserrat, and there's La Soufriere in St. Vincent. And as you can see, the ones in St. Vincent tend to be a bit more flatter, a bit more frisbee-like. And that's because the silica content is lower than the one here, which tends to be more steeper-sided domes. And then you can imagine the hazards posed by a steeper dome versus a flatter dome, because domes do collapse, you know. And so eventually, what happened in St. Vincent, this is a photo late in the eruption. The dome actually flowed and generated what we call a coulee. It looks like a big giant leech in the crater. So instead of going upwards mostly, it actually flowed laterally away from the crater. I mean, it's still a dome, it's not a lava flow, but it's called a coulee. But basically it gives you an idea of how sticky or non-sticky the magmas are relative to the lavas up here. All right, so just to give you an idea where St. Vincent is, it's located in the southern part of the arc. It's just north of Grenada. So it's more or less directly west of Barbados. Barbados is offset to the east of St. Vincent because Barbados is outside of the chain. St. Vincent is in the main chain. You know, very tiny island, as most of the Caribbean islands are. And that basically puts a significant number of people in harm's way. I mean, there were 20,000 people that needed to be evacuated if there was a problem from this volcano. Now, the thing about this volcano is, well, the good thing, if you want to see it, is that it's fairly busy. As you can see, it's erupted explosively, fairly regular over the past 1,000 years. Now, these are only the eruptions we can see in the record, the explosive ones. As I'll show you later, there could have been dome eruptions that we don't see because what happens is they don't get recorded because, as we'll see later, when this volcano started to explode, these two domes disappeared. It evacuated everything out of that crater. So domes don't get preserved in the record. Explosions do from the fallout. So we can see those. So this is quite likely that there were dome eruptions that we can't account for in here. So this is very busy for a Caribbean volcano because most of the others probably erupt once every few centuries. So this one we know enough about, and we were aware that it probably was going to be one that would erupt soon. That didn't say much though, because when the eruption started, it started very softly, for want of a better word. There were no earthquakes associated with it. And this was the photo that we saw that made us realize there was an eruption on, because that new black ice cream cone looking structure, that's new magma. That's a new dome coming up in the crater. So there were hardly any earthquakes.
Can I ask a question?
Yeah.
So how long would it take that new dome to form?
We think this was probably about 2 days old.
Okay, so very, very quickly.
Yeah, and just to give you an idea of scale, that's the crater flow we're looking at. And these walls are probably around 600 feet. So that dome is probably around 150 feet. Wow. From base to top in about 2 days. Wow. So it happened really quickly. So when we saw that, we knew we had to react. Now, one of the problems we had was because of how this volcano erupts. As you can see, there are different types of eruption. For example, in 1902, it was purely explosive. So there were earthquakes for, I think it was maybe 2 years of earthquakes, and then it just went bang, bang, bang for 2 years and then stopped. 71, it was purely effusive. It just built a dome very quietly. Most people didn't even realize it was erupting. 79, there was a hybrid eruption rather, which started with explosions and then switched to a dome at the back end. So when we saw this dome, there were a number of options. It was either going to be only a dome or there might be explosions after, although we've never seen that, but we couldn't have ruled out explosions coming. So when you see a new dome, one of the things you want to do is sample that dome, is to get a piece of it, to look at the chemistry of it, because that will tell you a lot about what you're seeing or where this magma is coming from. So we started to deploy the different instrumentation, because one of the things that we need to understand is that these countries are third world countries. So the instrumentation that is there now was definitely not present before the eruption. We had 1 or 2 instruments in, and that was it. The way how SRC works is more of an expeditionary body. So if there is a problem, then they'll beef up the monitoring networks, start putting in more instruments. so we can have a better look, but they won't have, quite a bit of permanent instruments in all the islands because the unit is funded by government donations from the Caribbean countries. And, as I said, people get complacent, and not just people, the politicians. So when there's no eruption happening, it's difficult to convince a politician to pay a stipend every year when there is no need. Well, he doesn't feel the need to do so. So there are times when we struggle with funding because people are not really willing to, well, the politicians from some of the countries are not really willing to pay until there is a problem. Because even Montserrat was guilty of that. They didn't really start paying until the eruption started. So it's an issue in the Caribbean that we have. So when we're monitoring a volcano, we're looking at different things. And basically, these are a function of how a volcano works. And basically, what a volcano is doing is bringing molten rock, magma, from deep to the surface. And in order to do that, it has to make space for that magma. And when it's doing that, it generates earthquakes. So we look at the earthquakes, which is the seismicity of the volcano. We use seismometers, which are instruments which measure the vibrations in the ground, to look at the earthquakes, the different types of earthquakes, as we'll discuss later. Now, that sort of activity will also deform the crust of the land wherever the volcano is. And you need to think in terms of volumes. So the current dome here at Montserrat is 200 million cubic meters. So imagine how much space that would need to take up if you bring it higher up in the crust. It will push the crust up. So we look at the deformation of the crust. We also look at the physical volcanology, but that needs to happen when there is surface activity, not before. So that comes into play after. Petrology and the geochemistry of the rocks, that comes into play after something comes into the surface. But the gases, there's always gases coming out. So we can measure the gases as well. So basically, we're looking deep, shallow, and at the top to try and figure out how much danger this volcano holds. Because our mission is basically twofold. There is research and then there is monitoring. When it's erupting, monitoring is priority. Keeping people safe, that's the priority. After that, then we switch back to research mode. During the time you're collecting data to aid your research, but you're not focused on research. You're focused on how dangerous the system might be to the population, and you're focused on getting the evacuation right, because that is quite important. Early evacuations cause problems.
Can I ask another question? So is the greatest risk the actual explosion of the volcano, or is it a potential tsunami in an area where so many people live so coastally?
It depends. It depends on how your volcano is set up. If your volcano is in a location where it can generate a tsunami from a dome collapse and there are communities vulnerable, then that is what you put your priority on. If there are communities in direct path of volcanic activity, then your priority would be on that. Luckily here, we didn't have a tsunami situation to deal with. What we were dealing with were these flows, these pyroclastic flows, these avalanches of hot rock and gases from explosion columns. Because if I go back to these two dome photos, as you can see, the domes in St. Vincent were contained within the crater. So there was no, even if they were collapsing, that would have been contained within the crater walls because they weren't big enough to come outside. Whereas in Montserrat, that is not the case. These ones are spilling out of the crater. So what's happening on the ground is relevant to how you respond. So we started our monitoring processes, as I said, and we started to beef up the networks. So this is a map of St. Vincent. The volcano here is in the north, this white looking mountain. That is not snow, that's just a topographical feature just to tell you the height of it. It's well in the north. Now, because these islands are small, it's quite difficult to get your volcano surrounded. Ideally, you want to surround your volcano, but because of where it is, we can't get instruments all around it. So we have to sometimes use instruments from other islands. It depends on how big the activity is. We can see it on other islands. So we install these seismometers within a few weeks of the eruption starting. I think by the 14th or the 15th, this network was in and ready to go. And basically what the seismologists were looking for, which are the people who look for earthquakes, sorry, wrong direction. They were looking for the different type of earthquakes that we were all expected to be seeing. So as I said, there are some earthquakes which signify the breaking of rock, and some earthquakes which suggest that you've got fluid moving around in the system. These are the low frequency ones, fluid being magma or gas. Those are bad news, because when you've got fluid moving freely, it means that your magma is on the move and probably on the way up to the surface. So normally the sequence starts with these groundbreaking events, which are called volcano tectonic events, which look like the regular earthquakes, but they're just very much smaller. And these are a function of rocks being fractured, and they're very high frequency at the onset. You know, when you start getting the low frequency events, that's when you start getting concerned about what your situation is with your volcano. So the idea was just to observe, look at what we're seeing, and try and come up with a theoretical model as to what we think was happening with this volcano, based on previous eruptions, but also what we were seeing at the time. The GPS network was also beefed up as well. And once again, you try and surround your volcano. And one of the things which the GPS does is it looks at the relative distance between two sites. And I'll show you a graph of the GPS just after the explosions, which will be really gold, just to show you how useful the sort of monitoring is. So basically, we were looking at the relative distance between the two furthest stations, the radial distance, just to see how they were moving apart or moving towards each other. So the idea is, if you're pushing up magma, you will actually dome the island up like a balloon, and those two stations will actually go away from each other. And as we'll see later, we'll see the recovery from after the explosion, after the volcano emptied its stomach and that space was evacuated. The volcano settled back down, and it's quite obvious in the GPS. So one of the things we were doing, we were looking at how fast this dome was growing. And it wasn't growing really fast. I mean, 1 cubic meter per second, you know, is really slow. And this was averaging around 2 cubic meters per second. The fast dome would be around 10, 11 cubic meters per second. Just to give you an idea of what a cubic meters per second is, I think a cubic meter is probably the size of a fridge, an average fridge. So imagine this volcano was putting out 2 of those every second in terms of magma. So that dome grew. And as you can see, we have different profiles over time as it grew. And you can see how it actually started to grow in a north-south direction. It got elongated with time. I think it was constricted to the east-west as well, because the crater rim was to the west, and the old dome from 1979 was to the east of it. So it had no choice but to grow in a sort of north-south direction. So this sort of slow growth may be significant, or it may not, because the idea is how fast your material is coming out should be a reflection of the energy of your system. So based on what we were seeing here, we weren't really convinced, or some people at least weren't convinced, that this was going to be a problem, because this was just like really docile dome extrusion. Now, for people like me who are geochemists and believe in the chemistry, my main focus was on the chemistry of that magma. And we took a sample on January 16th, and it was not where I expected it to be if it was fresh magma. So if you look at this, this plot I have here, this graph I have here, the 1979 magma these blue crosses here. If this was fresh magma coming up now after 1979, it should not be plotting in this region. It should be somewhere over here. It should be to the left of it, because magma evolved from left to right on this chart, if that makes sense. As they grow old, they move to the right. So what we were seeing was something in this dome. Sorry, I'm trying to move the cursor. In this dome, the 2020, the yellow squares are right next to the 1979, or slightly to the right of it, which suggested to us that it was more or less the same thing left over from 1979. This was not fresh magma by any means. This was all magma being pushed up really slowly. And that is why when I started to take measurements in January, I couldn't find any sulfur dioxide because it didn't have any. I'll explain that shortly. So these were two really important things. The chemistry of it wasn't right for fresh magma. It was too old chemically. And then the absence of sulfur dioxide, which is the gas which people mostly associate with volcanoes, was telling. Because if you have a magma, basically what this graph is, this little cartoon is saying that gases exsolve at different depths. They have different solubilities. So carbon dioxide and water comes off really deep, whereas sulfur only comes off shallow, around 7 kilometers deep. It doesn't come off around 20 kilometers. So if your magma is at 20 kilometers, it will still have all of its sulfur. It wouldn't lose any. It has to come shallow enough for sulfur to be soluble enough, or to become insoluble rather, and then it comes off the magma. So the absence of sulfur dioxide told us that this magma was too shallow for long enough, and it lost all of its sulfur. So that was a second piece of the puzzle that made us feel, okay, this was not really what we should be concerned about. Because if it doesn't have any gas and it's old, then it shouldn't be moving. So something was pushing it out of that reservoir. So there was something behind it pushing it out. So that was the mindset, at least for some of us, something is pushing this magma out to the surface. And when it gets to the surface, what is it going to do? Because that's the really important question. Is it going to continue building a dome, or would it explode? And we had no way of knowing that. So this is some of the gas data I've been collecting. And as I said, the last data I had before was 2018 rather. So basically what this plot is doing is telling you where your gas is coming from. So just to give you an idea, HD means hydrothermal, DHM means hydrothermal and magmatic. Anyway, you see M, it means magma is involved. So these four areas here, you've got a magma involved. This is when you're just a hydrothermally dominated volcano, when it's just sitting there not doing anything. There's no fresh magma deep coming in. So when I took the first measurements in January and February, I saw a switch from a system that was at rest to a system with magma in it. So this is one of the reasons why we monitor during peacetime. So this was quite important because I saw this switch. So that even convinced me more that, okay, we had a problem. It was deep, we can't see it, but it's there. There's definitely a deep magma pushing this lava out in this dome. None of us knew when it was going to happen. And none of us knew what it was going to bring. But we sort of knew that there was something coming. So, let me just say, I spent 6 months there. So I got there in January and I stayed until the end of the eruption. So I saw more or less all of it, apart from the first 13 days of it or so. I saw everything. So I was involved, collecting data continuously, and looking at what was happening. So after all of that guesswork, we started getting what was considered a buildup. The earthquakes started to get more intense. The plot on the left is a plot from March 23rd or 24th, yeah, March 24th, when we had a series of events. And on that day, we were actually called off the mountain. We actually had to run, well, not literally run. We had a helicopter come and pick us up. There's video of that, us scrambling off the mountain, because we got a call from the seismologist saying, you know, leave now. So we were trying to install the instrument at the time, a gas instrument, you know, and after that, it more or less died back down. It didn't really do much until April 5th, which was a day after this photo was taken, because we went to the summit on the 4th, which was the Sunday, a few days before it exploded. And then, as you can see, the dome is looking a bit different now. It's no longer flat in the center. It's pushed up a bit, and there's a bit more fire visible around it. So that was an indication that, you know, things were changing. It wasn't the normal chugging along 2 cubic meters per second. It was going a bit faster. And then the earthquakes that you can see on the right, which was the day after, that more or less, the person who was the director at the time, because we were doing rotations of 1 month. So I did February, and that was it. I was there after that. So the director at the time, the current director, which was Professor Robertson, he said, look, you know, we need to stop the field work. Do not go back onto the mountain, because this is not good. So I went home, because we were living in the village about 3, and Professor Robertson, me and him lived in the same house. But given that he was the director, then he needed to be up there. I didn't. I couldn't do any field work. So I was home looking at the drums and wondering, you know, well, when is this going to happen? I just did not know. So on the morning of April 9th, the explosion started. There was one isolated explosion. Let me just go back a bit. By the Wednesday, we were convinced that something was going to happen, which was the day after those earthquakes, 2 days after those earthquakes, sorry, because the earthquakes was on the Monday. So we decided to evacuate on the Thursday evening at 6. Then there was also a decision to do 24-hour shifts. And there were only 3 of us, because my student, she's not an employee, so she can't be allowed to do shifts, and it would be asking too much of her. That's a lot of responsibility to ask, to put on a student. So we had 3 of us. He had Rod, he was a seismologist, Professor Robertson, and myself doing 8-hour shifts, you know, continuously. So Rod was doing, well, the days. Professor Robinson was doing from 6 till midnight, and I was doing from midnight till 6. So the first shift I did was that night, which was the Thursday night. So I got down into the village around just after 7, went to a bar, had a drink, decided to sleep for a few hours. The plan was to sleep maybe until around 11 and go back up to the observatory just to have a look, because it was a bit intense at that time. I think I probably laid down for around half an hour when I heard, oh, was obviously an explosion happening. And I was really tired, and I did not want, I wanted to be sleep. I just needed to sleep. You know, I was not happy that I had to leave. But I came outside, saw the plume in the air, and I was like, okay, cool, go and pack your stuff and go. So I did that. There were some guys in the village as well, because everyone did not leave. There were some guys who were pretending to be quite brave. And the night before, they were speaking to me, and basically their mindset was, if I'm not leaving, they're staying as well. You know, I relate to them that this was my job. You know, I needed to be here. So funny enough, when I came out the morning, those guys they had their bags in the back of the truck already, ready to go. They were not staying any longer. They were just like, let's go now. So I took my stuff and I drove up, drove really slowly because there were still people in the village, and the plan was not to panic anyone, even though I was eager to get up to the observatory so I can see it. But I took my time. I went out, dropped them off so they can head to where the evacuation place was. And we went up, and basically what was happening was not what we expected, because we get different types of explosions from these volcanoes. So you can see a few words here like Plinian and Volcanian, and it just has to do with the intensity of the energy of these eruptions. So these subplinian eruptions, as they're called, basically they're so powerful that everything is pulverized to ash. And that went on for 3 days. And they were pushing the ash columns so high that that's when ash started falling on Barbados as well, and also back on to the island, because ash is controlled by wind. So wherever the ash goes, the wind will push it in whatever direction the wind is blowing in that part of the atmosphere. So as it gets above the inversion layer, which is around 15,000 feet, the winds here start going to the east. Normally they go to the west below that. So anything below that will go to the west, whereas above that, it goes to the east. So Barbados got ash for the first few days, and so did the island of St. Vincent, because these eruptions were so huge that you basically had them umbrellaing out these ash clouds, and they was just like raining ash back down on the country. And that may not seem like a situation, but it was a problem, because if it dumped 50 feet of ash where we were, the place would have become unlivable. So on Saturday evening, which was 2 days into it, or day and a half into it, sorry, there was some discussion between me and Professor Robinson about pulling back from the observatory, because we were 9 kilometers from it, which is, it's not that far, So the activity was going, because we were expecting something closer to 1979, which is these Volcanian style eruptions, which are isolated bangs. There's a bit of rumble, and then it's done. And there's one, maybe a few days later. Oh no, we weren't expecting 23 eruptions in 2 days, especially these really huge, intense eruptions. So that, I think, it scrambled my brain, for want of a better word, when it was going on, because this volcano here, the one in Montserrat, it's never done that. Well, at least not in this eruption. So I've never seen that style of behavior. So that was a first for me as well. And it's a much bigger volcano than ours. It's huge and it's imposing. It's menacing. And at night, it was really, really, I don't want to say terrifying, but it got your attention at night when it was making these noises, and you couldn't see. So your mind was just playing tricks on you as to what it was actually doing. But basically, we had this really intense bit of activity for the first few days. And then around Sunday evening, it started to slow down. So first, that was good news. Okay, so it started to lose energy now if it's slowing down. And then it switched back to, or switched to these style of explosions, which we call volcano, which are these really isolated bangs. You get these mushroom clouds. And then that was, the first one was the Monday morning, which was the 13th, or the 12th, sorry. That should be the 13th, not the 12th. And then over time, as we can see, the space in between each explosion got longer, which was also an indication of the system losing energy. So it was running out of steam, basically. So for the first few days, it was going really hard. And then after a while, it started to give you these isolated explosions. 2 on the first day, then 1, then the next one 2 days apart, until it stopped. So basically, you can see it losing energy over time from this plot. To be fair, on the first 2 days, I mean, none of this was in our minds. What was in our minds was how much ash was going to be dumped on the area that we were living in. We were actually living in there, and well, we stayed in the ash. Well, I stayed in the ash until I left, which was probably 2 months. So we lived in the ash throughout the whole time. Yes, we couldn't leave. Sorry. So yeah, so just to show you, so this photo on the left, this was the explosion from the Monday morning. This is one of the volcanions. This is from 9 kilometers away. So you can see this size, the scale of the explosions that were happening, and the sound was just amazing as well. And this village on the right is the village that we lived in. So this was taken after one of the explosions, and you can see it's like it was dusted by a crop duster, but that's ash, you know. And what ash is basically is pulverized rock. So it's not really a good thing to be breathing in fine rock dust because there's glass and stuff in it, you know. But there were some people who did not leave for whatever reason. They stayed in the ash. You can understand why for some people, because most of these people were farmers, you know, so their livelihood was their animals and their crops. So it was difficult for them to just walk away from that because they wouldn't be able to make any money if they weren't doing their farming. So this is the plot I spoke to you about, this deformation plot. So as you can see, basically what we have 3 different axes on this GPS instrument. There's a north, south, east, west, and then up and down. So it's a 3-component instrument. That's what they call it. And as you can see, after the explosion, this is a plot just before and just after the explosion. You can see that all components of the station jumped back down. And basically what that shows is that the magma that came out and generated that explosion would have taken up a bit of space in the upper crust and deformed it. And now it's no longer there. The crust is relaxing back to where it was initially. And that was probably a good indication that, okay, it was probably done because it's gone back to a flat line. It wasn't still going down. If it was still going down, that would probably be slightly something different. It would mean there's probably more there to come out still, but it just went flat. So that was a good indication that, okay, it's erupted what it wants to erupt and it's done now. But there was still gas coming out. So I was looking at the chemistry of it as well. There were a number of instruments I was using, you know, but you can see it switched back to what it was in 2018. It switched back to over here, which was good news. So the magmatic component that we were seeing, it's gone. It's no longer there. There was still sulfur dioxide coming out as well, which lasted until around November of that year. But that was residual sulfur. And as you can see, it was always on the way down. So this graph has tells me 2 things. It tells me that there was probably one batch of magma that came up, erupted. That's why the sulfur fell away like that. It wasn't pulsating over time. It wasn't being replenished. And it also tells me that the eruption has stopped because sulfur has disappeared. Again, now in the initial parts of the eruption, someone would argue, there were some arguments that because there was a dome, it was acting like a plug to stop the sulfur from coming out. That is not the case now. So no sulfur means there's no sulfur from the source. So that this sulfur issue, the GPS, I think those 2 pieces of information was definitely enough for us to declare the eruption over and done with. So whenever these volcanoes erupt, we have to we have what we call is the eruption model, because it helps us understand how the particular volcano behaves. And basically, we need to have an idea of what we think the next eruption is going to be like. Not so much when. It depends. Some people try and think when. But for people like me, behavior is more important because, as I said, the people of St. Vincent are well educated. There are definitely outreach programs there. And I witnessed the evacuation and it was very organized. People knew what they had to do. The bags were already packed, obviously. So when the order was sounded, they took their bags up. They went to the points, got on buses or the ships, and they left. So the idea is to get people used to the fact that you live in a volcanic environment. But if you understand what needs to be done when there is a problem, all should be well. Because the islands are quite tiny and you can avoid volcanoes. And another thing about them is they provide very fertile land. So for people who are farming, they're going to gravitate to these areas because the land is quite fertile. So basically, the model that we came up with, that we had this lower chamber, this lower reservoir, you had this fresh magma, as we call it, the one that generated the explosions down there. It was sitting down there for however long, probably a long time, probably a few thousand years. Some of it came up for whatever reason. We're still trying to figure out what triggered this eruption because we haven't seen any signs of mixing. Normally when volcanoes erupt, normally mixing is the culprit, whereas you have hot magma coming from deep, heating up a cooler one, it erupts. We didn't see any evidence of that here in the rocks. So we're thinking something else because there are other reasons why volcanoes may erupt, but not as commonly as mixing. So that will be part of the model eventually, So basically we had this magma that was driven up to the surface. Then it started to push the old residue from 1979 out and built this dome. Now, because St. Vincent is a very water-rich country, loads of rivers, loads of rain, especially during the hurricane season. And because there was probably a plug, we couldn't see any sulfur at the surface because sulfur reacts with water really easily, sulfur dioxide. If it sees water, it mixes. So you lose it in the emissions. However, when that old magma goes out of the way and the fresh magma could degas, then is when it released the sulfur. So the very first sulfur measurement I was actually able to take was on April 8th, which was the afternoon before the explosions. So by that time, it was shallow enough for it to be releasing enough sulfur to overcome whatever water was in the system. And it was enough sulfur for me to measure. So that was probably another indication that there was a problem coming, which was the day before. So what we try and do is not necessarily predict eruptions. What we do is we react to activity, because as I basically confessed that this eruption caught us off guard. We knew about it 2 days after it happened. So there were some tourists up there on the 27th of December who actually saw the ground being split. It looked like a very large ant mound. We got the photos a few weeks later, but if you didn't know what you were looking at, you wouldn't have a clue. So we requested that some guys who work at the local NEMO go up there on the 29th, and they sent us that photo, which I showed you. And then we knew that there was an eruption. So sometimes you can't see them coming And luckily for us, it didn't start explosive. But you kind of get the impression that if it was going to be explosive from the start, there would have been much more earthquakes as well. Because these energetic magmas, the gas-rich ones, which are more willing to go explosive, they don't really come to the surface slowly. They come with a lot of energy, momentum. So they announce their presence. So it worked out how it worked out, whereas it started slow. It gave us enough time to beef up our instrumentation. And to be fair, it sort of made us look good in the end, because the evacuation happened 16 hours before the explosion. You know, I mean, none of us knew it was going to explode Friday morning. We just knew it was going to explode soon. I couldn't tell you exactly when, but we knew, okay, soon, maybe within 2 or 3 days tops, but not the very next morning, because I think if we knew it was going to explode the Friday morning, we would have probably evacuated on the Wednesday. I mean, 16 hours is a bit tight, you know, and probably a bit too close for comfort. But that is how it worked out, basically. Sometimes you need luck with these things. So, yeah, that's it.
All right. Well, that was so fascinating. What an amazing thing to have lived through. So, so I have a question from YouTube. So Cindy wants to know, how much of the chemistry analysis that you do, how much is that integrated with prediction modeling?
Well, it wasn't done by us. We have colleagues overseas, because you need labs to do that. It basically, as I said, it helped us to realize that this was not, this magma that we were seeing at the surface was not the one we should be focused on. It was what was pushing it out. So in this situation, it was quite useful, because, you know, because of where it was, and we had previous data from the most recent eruption, we could have done a direct comparison to the 1979 lavas, the chemistry of them, and say, look, this is more or less the same lava. It's not more basic or younger, I should say, than the one that came up in 79. So that more or less made us rethink the model of what the volcano was doing. It's not the one that's coming out is the problem. There's something pushing it, because that one was basically dead. It was degassed, you know, so it, as I said, it shouldn't be moving on its own. There should be no energy to move it.
I think that the mystery of it is so intriguing, right? That you have the old stuff being pushed up, that it shouldn't be moving, right? So that's kind of cool. So Glenn here in the theater has a question.
Just for clarification, is a dome like a soap bubble, hollow in the center, but rust over the top of it, or is it more solid all the way through?
So his question is the dome like a soap bubble where it's kind of hollow inside with the crust around it, or is it solid?
It's solid true and true. In some domes, maybe the middle of it might be molten, but it's solid true and true. It basically is just an ugly mound of rock that's just oozing out and piling up around the vent mouth. So it's very disorganized. There's probably not much structure to it, although sometimes you get these lobes growing in some domes. But this one was just like really solid basalt rock, you know. So even if you try to drive something through it, you couldn't, like an object through it. You couldn't push a metal rod into it. It was just solid rock at the edge of it. So what we were doing, basically, we weren't really actually directly sampling from the dome because it was too hot to do that. So you would wait for stuff to roll off of it within a few tens of meters of it. And then basically you had someone there with a bucket, and then one guy would run close to it, grab a few pieces, run back, and then we'll smash them up and stick them in the bucket, run back to the helicopter and leave. So you try and minimize how long you're there, because if a large enough chunk falls off, then all of us are running for our lives from that rock fall, because you get boulders the size of this room coming off of it. So yeah, if that comes down, then, you know, we're scrambling. So you don't want to get too close to it, especially because it's above you as well. So
and that's what's, yeah, and that unpredictability, I think, must be really scary too. Right, well, when you're trying to study it.
Getting hit by a rock while you're trying to sample a rock.
Right.
So
A hot rock.
yes.
The gases decomposition of the rock as it reaches the surface or something else?
Is the source of the gas the decomposition of the rock, or is it something else?
No, basically the gases were trapped in magma from they're created. So basically, as rocks have gases in them. So when you melt rock, you generate a gas in it at the source. And sulfur is definitely one of the more obvious ones, but the truth is the most common gas in volcanic emissions is water and carbon dioxide. Between them, you'll probably have around 85% of your emissions, sometimes even 90 actually, or a bit more, is between carbon dioxide and water. Your sulfur gases make up of around 7%, whereas your halogens are around 1 or 2%. Now, as I said earlier, when these gases come off, has a lot to do with where the magma is. So if it sits really deep, if it stays deep at 20 kilometers, the only thing you'll see is CO2 and water. You wouldn't see any sulfur. So that's why we're not seeing any sulfur now. It doesn't mean that there's no magma deeper, but it's not shallow enough to push sulfur out of the exsolution, out of the liquid. So it's actually in the liquid, trapped in the liquid, but it needs lower pressure or crystallization to drive it out. Because when you crystallize the magma, you use up the liquid, and then you have less liquid to accommodate the gas. So it's just like gas in a fizzy drink. You can push gas into a liquid, but as you decompress that liquid or use up the liquid, then the gas has to come out of it. So what's happening is as the magma is getting shallower, the pressure is dropping, so that's encouraging degassing, but it's also crystallizing as well, which is using up liquid. So there's less room for the gas to be trapped in. So those two processes are pushing gas out of it as it comes shallower. And which gases you're seeing is relevant to the depth. So if you're seeing quite a bit of hydrogen chloride, it means your magma is probably around 2 kilometers, because it only comes off really shallow. So which gases are dominating your chemistry and the ratios between them could give you an idea of which part of your system is dominating your degassing. And then it gives you a good idea of what you're dealing with.
All right. Well, I think that's all our questions. Thank you so much. And thank you so much for joining us for Rocktober here at the North Carolina Museum of Natural Sciences. Until next time, thank you, Thomas. Thank you, Chris, for making the magic behind the scenes. And thank you to our audiences, both online and in person. Have a great afternoon.
You too. You're welcome.
Bye-bye.